Today we're extremely excited. We have Houman Owhadi from Caltech visiting us. We know each other since basically he joined Caltech from the early days. The only thing I can tell you to summarize what he does, whatever he does, he puts the word optimal in front of it. So if he works on uncertain quantification, it's optimal uncertain quantification. So Bayesian inference is optimal Bayesian inference. And this is the way to get reaction back. And hopefully we will get some of that today with your talk on, again, theoretic approach to numerical approximation and algorithm design.
Thanks, Nicolas. Thanks for the introduction and thanks for the kind invitation. Various parts of this talk are going to be joint work with Florian Schaffer and Clint Scoville from Caltech, Tim Sullivan from the Free University of Berlin, and Lei Zhang from Shanghai Jiaotong University. So this talk is going to be mainly about interplays between numerical approximation and Gaussian process regression. These interplays are far from being something new, but we're going to look at them from a game theoretic perspective and see if we can learn something new about them. The setting that we are going to consider is that of a linear, symmetric, positive, invertible local operator that we're going to call L, mapping some suborder space HS0 of omega into its dual space H minus S of omega, where omega is some regular bounded domain of Rd. And by this operator L being local, we simply mean that the operator scalar product between U and V is 0 if U and V have disjoint supports. We are going to call G the Green's function of that operator defined in a weak sense. This simply means that if you look at the solution of the linear system LU equals F, it can be obtained by integrating this Green's function against F. Okay? So this Green's function is a symmetric positive definite kernel, so you can look at it as the covariance function of some underlying centered Gaussian process that we're going to call Xi. Okay? Now, when S, the regularity of the sublet space, is larger than the dimension of the space over 2, this Green's function is continuous in X and Y. This simply means that this Xi is a centered Gaussian process in a classical sense, and the covariance between Xi at the point X and Xi at the point Y is simply G of X, Y, okay, where G is your Green's function. If S is smaller than D over 2, this Green's function may be discontinuous, and you have to define this Gaussian process in a weak sense by integrating it against a tensor function in H minus S of omega. And then this integral is simply a centered Gaussian random variable with variance the double integral of phi against G. Okay? Now, to illustrate the connection between this Gaussian process and numerical approximation, let's look at a simple problem. So assume first that S is greater than D over 2 so that the elements of this sublet space are continuous. And assume that you have an unknown element of HS0 of omega. But you are given its values at m points. Let's call them x1, x2, xm. Those are m points of the domain omega. And you are asked what is the best approximation of U. And here you define best in the sense of minimax using the relative error in energy norm of the operator as a loss. Well, it turns out that your best approximation of U in that sense, after seeing the values of U at those m points, is obtained by taking the conditional expectation of that Gaussian process C that we have just defined, conditioned on the values of U at those m points. Okay, xi's. Okay, so this is an example, but it can be generalized in a game theoretic setting where you have two players playing an adversarial game. Let's call them 1 and 2. One chooses an element u of hs0 of omega. He doesn't show it to player 2, but player 2 gets to see m linear measurements on u that we are going to represent by taking the duality product of u with m elements of the dual space. We are going to call them phi1, phi m. And the task of player 2 in this game is to guess what u is. Okay? Now the guess of player 2 is obviously a function of this m linear measurement, so we are going to call it v. The choice of player 2 gets combined with the choice of player 1, and player 2 receives a loss, which is measured here as a relative error in operator norm. Okay, so in the energy norm defined by the operator L. And the question is, if you had to play these games many, many times, how would you play it? Okay. Now, first, before I answer that question, why should we care about this game? The reason why we should care about it is because if you are a numerical analyst and you try to compute fast, or you try to compute at all, you have to compute with partial information. So you have to bridge the discrete to the continuum. And you have two ways of bridging the discrete to the continuum. You can guess how to bridge that, and this is actually the popular method. Or you could try to find some kind of optimal way of bridging the discrete to the continuum, and here you can define the notion of optimality in that game theoretic setting. Okay, now we know from the early work of von Neumann that when you have an adversarial zero-sum game, optimal strategies are going to be mixed or randomized strategies. So this, you are going to see the same thing here. So it turns out that here the optimal strategy of player 1 is to select u at random according to the distribution of that Gaussian field or Gaussian process Xi that we have just defined. And the optimal strategy of player 2 is to assume that player 1 is selecting u according to that distribution and define his optimal bet by taking the conditional expectation of Xi with respect to the m linear measurements on u. Okay? So this is a pure strategy and it is an equilibrium for the game in the setting where you lift this minimax that you have in the game to measures on the possible choices for player 1 and measures for the possible choices for player 2. You can also show that this optimal choice of player 2 is also optimal in the deterministic worst case setting of optimal recovery of Micheli and Rivlin. So it is the solution of the inf soup problem. Okay. Now, since you're obtaining this optimal choice of player 2 by conditioning a Gaussian process or Gaussian field, you can write this conditional expectation as a linear combination of the covariance function of the Gaussian process integrated against the measurements. This is a classical representation theorem. It's a classical result. And these coefficients are obtained by inverting this matrix theta, which is a Gramian, obtained by integrating this measurement function phi against the Green's function. Now you look at this expression and you massage it a little bit and you realize that you can write this function v as a linear combination of these measurements that you have made on u. So those are the duality products of vi with u. Those are the linear measurements. And the coefficients entering in this linear combination are deterministic functions corresponding to optimal recovery splines or elementary gambles or bets for playing the game, depending on whichever way you want to look at them. So as optimal recovery splines, they are simply obtained by taking these elements of the dual space and pulling them back by the inverse of the operator and taking linear combinations of them with the inverse of this Gramian that we have defined before. And as elementary bets, this psi I is simply the best bet of player 2 on what U is, given the information that the duality pairing of U with phi j is delta ij for all j. Okay. Now, the last point is that these phis and psis form a biorthogonal system in the sense that the duality pairing of psi I with phi j is delta ij for all I and j. And the orthogonal projection of U, so this is orthogonality with respect to the operator scalar product, onto the pullback by L-1 of the linear space spanned by the phi minus 1s has this very simple expression. Okay. So those are some elementary points on the connection between Gaussian process regression and numerical approximation. And what I want to do now is to illustrate these points by addressing some problems related to numerical approximation. The first problem that we're going to look at is a problem in numerical homogenization. This problem can be formalized as follows. Given a number m, you want to find m basis functions, let's call them psi1, psi-m, that are as accurate as possible in approximating the solution space of this operator L. And you want also these basis functions to be localized. So you want them to be as localized as possible. Now, this problem is non-trivial because if you want the most accurate functions, those are going to be the eigenfunctions of your operator associated with the lowest eigenvalues, and those functions are typically completely delocalized. And this is actually the kind of problem that people are also trying to solve when they try to construct Wannier basis functions, which are essentially linear combinations of eigenfunctions that are localized both in space and in eigenspace. So this is more or less what we want. Okay, so this whole field is called numerical homogenization because these kind of problems can be traced back to pioneering work in classical homogenization. And the localization problem is a subfield of its own in that area. And what I want to show you is that this problem has a very, very simple solution from this Gaussian process perspective. You simply take your domain omega and you partition it into subsets of size or resolution h. Okay. And you take your phi i's, so these measurement functions, to be weighted indicator functions of these subsets, or masses of Diracs centered at these subsets. Then you take your Gaussian process, you condition it with respect to these phi i's, so you basically compute, let me go back, you compute these guys, or these guys, depending on how you want to look at them, and you get these elementary bets or gambles or optimal recovery splines that you call psi-i's, and these guys are going to solve this numerical homogenization problem. In which sense? Where they're going to solve it in the sense that they achieve the Kolmogorov n-width accuracy up to a multiplicative constant, meaning that they will achieve the same accuracy as the m eigenfunctions associated to the m lowest eigenvalues up to a constant, and they decay exponentially fast from the support of support of tau I. So they have this exponential decay that you can obtain rigorously and that you can also observe numerically. Now, from the Gaussian perspective, Gaussian process perspective, from this numerical approximation result, you also learn something about the underlying Gaussian process. So again, when your masses of Diracs, when your measurement functions phi i's are masses of Diracs centered at these points, your optimal recovery splines or elementary bets are these functions psi i's obtained by conditioning the Gaussian process to be at values delta ij at those points xj's. So basically what you learn is that if you take this Gaussian process and you pin it to be 1 here and 0 at all these points, you get exponential decay. And this is not something trivial because you have a representation formula for this optimal recovery splines as linear combinations of these Green's functions. And this Green's function has an algebraic decay, but when you take this linear combination, you have a cancellation effect, and you get an exponential decay. Now, another thing that you learn is a rigorous proof of a phenomenon known empirically in kriging as the kriging effect. So what you can show is that the correlation between the Gaussian process at the point xi and xj condition on the Gaussian process at all the other points is equal to the minus the angle between the spline psi I and psi j. And because you have an exponential decay in these optimal recovery splines, you get an exponential decay of this conditional correlation. So the idea here is that by conditioning on the points in between, the Gaussian process at these 2 points, x and xj, gets decorrelated. So those xi of xi and xi of xj become nearly independent. You can say the exact same thing in the situation where your measurement functions are indicator functions of these subsets twice. By the way, in that case, the interpretation of psi I is simply that psi I is your optimal bet on what u is. If I tell you that the integral of u in the square I is 1 and 0 in all the other squares, and this is what this psi I will look like. Okay? And you also get this screening effect. Okay, now let's look at another problem in numerical approximation. So in this other problem, we want to construct operator-adapted wavelets for this operator L. And by adapted, we mean three things. We want those wavelets to be scale orthogonal with respect to the operator scalar product. Why? Because if you write your operator in the basis form by these wavelets, then you will get a block diagonalization of your operator. Next, you want the operator to be well conditioned within each subband formed by these wavelets. Why? Because then each one of these blocks will be well conditioned. And third, you want those wavelets to be localized in space. Why? Because then those blocks will be sparse or nearly sparse. Now, operator-adapted wavelets are not something new. In fact, since the inception of wavelets, people try to apply and adapt wavelets to operators. And you will find several generations of these operator-adapted wavelets. The first generations of operator-adapted wavelets were shift and scale invariant, so you could not really adapt them to inhomogeneous coefficients in your PDEs, or you cannot really adapt them to boundary conditions. The second generation, with the second generations of operator-adapted wavelets, people tried to get all these three properties. But typically, the way they were getting orthogonalization is by using some kind of Gram-Schmidt orthogonalization. So they were forcing their way into it. And by doing that, you can get two properties, but the third one typically goes out of the window. So do you have a simple way of getting all three? And that's the question here. Well, it turns out that this problem of numerical approximation has a very simple solution from that Gaussian process perspective. And the solution is simply to take R pre-wavelets in H minus S of omega. So this is what these R pre-wavelets look like, and consider them to be a hierarchy of phase. Then take your Gaussian field Xi that I have defined in the beginning of this talk. This Xi is going to contain all the information that we need to solve all the numerical approximation problems that we have about L. And condition this Xi on those phees, and then you get a hierarchy of psis. Those psis are going to act as L-adapted pre-wavelets. And then you can take local differences between these pre-wavelets, and you're going to get L-adapted wavelets in the sense that I've defined in the beginning, right? So these things are going to solve to have these three properties that are desirable. Now, this is at a very high level, so let me make what I've just said a bit more precise. So the first thing that you do is that you give yourself a hierarchy of phase, a hierarchy of nested phase. By this, I mean that you give yourself a hierarchy of elements of the image space H minus S of omega, and you assume these guys to be nested in the sense that level K phase are linear combinations of level K plus 1 phase, right? Then you take your Gaussian process and you condition it with respect to this phase, and you get your gamblets, elementary beds, or your optimal recovery plans, again, depending on how you would like to look at them. And you get them by pulling back this phase by L minus 1 and taking linear combinations of them with the inverse of this Gramian. Okay? And you get this hierarchy of psi's. This is, so for example, for phase you can use Har-pre wavelets. For instance, if your domain omega is this unit square of side 1, you can take your phase to be weighted indicator functions of a hierarchical nested partition of your domain of resolution 2 to the power minus k. So at level 1, you are going to have 4 of these phase. At level 2, you are going to have 16. At level 3, you are going to have 64. And you can see that this the indicator function of this set is a linear combination of these 4, and the indicator function of this set is a linear combination of these 4. So you have this nesting relation, and what you see here is one of the rows of that matrix pi expressing this linear nesting relation between level K minus 1 phase and level K phase. Okay, and this is what those phases look like. Those are your classical Har-pre wavelets. If S is greater than d over 2, then you have enough regularity in your solution space, and the elements of your solution space are continuous. So you can take your phase to be masses of Diracs. More precisely, you can take your hierarchies of phase to be subsampled Diracs. So here at level 1, you only have 1 Dirac. At level 2, you have 9. At level 3, you have 81. And this guy is subsampled from this 9, and those 9s are subsampled from this 81. So in that case, that matrix pi is really elementary. Its entries are zeros or ones, okay, because you are doing a subsampling. This is what these psi's look like over 7 levels of resolution. So again, they are obtained by pulling back those phase by L and taking linear combinations with the inverse of the Gramian. They look like pre-wavelets, and they are going to act as L-adapted pre-wavelets. And because those phase are linearly nested, and because you obtain those psi's by pulling back the phase by a linear operator, those psi's are also going to be linearly nested. So you can compute your level K psi's from the level K plus 1 psi's using some underlying interpolation matrix that we are going to call R. Now, in practice, at the end of the day, I will show you that you can compute those operator-adapted pre-wavelets in near-linear complexity in n polylog n complexity. And the reason why you can do so is because you never actually compute L minus 1 of those phis. You use this nesting relation, and because those guys are exponentially localized, those interpolation matrices are going to be sparse or nearly sparse. So you can do this computation very fast. Okay. So if you call Vk the linear space spanned by those psi-k's, because those psi-k's are linearly nested, then Vk minus 1 is the subspace of Vk. So you can do typically what you do with wavelets. You can call Wk the orthogonal complement of Vk minus 1 in Vk with respect to the operator scalar product. And you have the following orthogonal decomposition of Vk. And you also have the following orthogonal decomposition of your solution space Hs0 of omega into subspaces that are mutually orthogonal in operator scalar product. Okay, so you get a multi-resolution decomposition of your solution space. And the question is, what are the basis functions for these subbands, WKs? Okay, and those basis functions are going to be your operator-adapted wavelets, so we need to identify them. What are they? Okay, so first, those elements of WK are by definition going to be orthogonal to VK minus 1, and being orthogonal to VK minus 1 is equivalent to having duality product with the VK minus 1 equal to 0. And since they are in VK, they can be written as a linear combinations of the psi k's. So therefore, chi is in this WK if those coefficients C are in the kernel of this matrix pi that is expressing the linear dependence of phis at level k minus 1s to phis at level k's. So basically, you can show that you can obtain those operator-adapted wavelets by taking the linear combinations of those psi's with coefficients whose rows are spanning the kernel of this matrix pi. Okay, and again, this pi is the pi that is expressing the linear dependence of level k minus 1 phis on level k phis. Okay. So in practice, what you do is that you simply take local differences of these psi's. So if this is one of the rows, those are the entries of one of the rows of pi's, you are going to have 3 corresponding chi's that are formed by looking at the 3 vectors that are orthonormal between each other and orthogonal to this vector. Okay, so you have 3 of them, and basically, again, what you are doing is that you are taking local differences of these psi's. And this is what these orthogonalized wavelets look like. Okay, again, over these 7 levels of resolution. Okay. So those operator-adapted wavelets are scale orthogonal, which is one property that we wanted. They are also exponentially localized. Why? Because we have seen that those psi's are exponentially localized. So if we take local differences of them, we are also going to get things that are exponentially localized. We need a third property. We need the operator to be well conditioned within each subband. For that, we are going to look at the stiffness matrix of the operator in the basis formed by these orthogonalized gamblets, chi's. And then one thing that you can show is that the condition numbers of the stiffness matrices is uniformly bounded in K. Okay? And this is something that you can show rigorously and you can also observe numerically. So if you call AK the stiffness matrix of this pre-wavelets psi's and BK the stiffness matrix of these wavelets chi's, you can show that the stiffness matrix of this psi's has a condition number that blows up with K, whereas the condition number of these BKs remains uniformly bounded. So this is what this figure is showing. It is showing the condition numbers of the BKs in blues and the condition numbers of the AKs in yellow, and this is in log scale. What this figure is showing is the range of eigenvalues of the operator over the whole degrees of freedom. So you have n degrees of freedom, and this is the range of eigenvalues of the operator. And those are the ranges of the eigenvalues of the operator within each subband. So you get something that looks like and quacks like an eigen subspace decomposition, but it is only an approximation thereof, okay? Because although you have orthogonality in operator scalar product, these subbands are not orthogonal in L2. But you get something, some kind of approximation of an eigen subspace decomposition that you can compute cheaply, right, in n polylog n complexity out of this. Okay. So to compute those wavelets, you actually need to identify those operator adapted, you need to identify those interpolation matrices R. And the way you identify them is by simply saying that, this guy is a linear combinations of this size and also these chi's, and you need to satisfy these constraints stating that the phis and psis form a bi-orthogonal system, and this the psis at level k minus 1 needs to be orthogonal to w at level k. And this gives you a linear system for your coefficients, and if you solve it, you get this interpolation matrix. Okay. Now, the interesting thing about this interpolation matrix is that, so it has a game-theoretic interpretation. I'm not going to go over it, but what I want to observe is that it can be computed fast, because this pi is, so if you take our pre-wavelets, this guy is sparse. This is the identity matrix, is sparse. This is the stiffness matrix of this psis, and because these psis are localized, this thing is sparse. This is the W, this is sparse. Now this BK is the stiffness matrix of these chi's. These chi's are localized, so this B is sparse, and it has a uniform bound on its condition number. And if you have a matrix that is sparse and well-conditioned, its inverse is going to also to have the same property. Okay, if you have a good notion of distance, which is the physical distance here. So this thing is sparse, and you can compute it fast. Okay, so at the end of the day, you get a wavelet transform, L-adapted wavelet transform whose complexity is n polylog n, where the power in the polylog is 3 times dimension. Okay, now the algorithm is a deterministic algorithm. And what we have done here is to use the Gaussian process regression approach to identify what this algorithm is, right? Once you have identified the algorithm, in fact, you can pull the Gaussian process regression part under the rug if you wish, or you can keep it if you want to do some uncertainty estimations from a Bayesian perspective on your numerical errors. Okay. Fast solvers. So here is another problem that you will find in numerical approximation. So many wonderful fast solvers have been developed and out there, but the specific question that we are going to ask is can we find a fast solver that has some degree of universality? And by this, I mean, can we find a fast solver that we can apply to an arbitrary symmetric positive continuous linear bijection mapping HS0 to H minus S, okay? And this is a non-trivial question because the class of such operators contains elliptic operators with rough coefficients, and we know that if you just use a geometric multigrid for PDEs with rough coefficients, you can have robustness issues, okay? The convergence rate can break down with discontinuous coefficients. Well, this problem has, again, a very simple solution if you look at it from this Gaussian process regression or game-theoretic perspective. You simply compute these L-adapted wavelets, and you write your operator in the basis formed by this operator adapted wavelets using a finite element method. Okay, and what these wavelets will do is that they will decompose the solution space of your operator into subspaces that are mutually orthogonal with respect to the operator scalar product. Now, from a numerical linear algebra perspective, what they will do is that they will take the matrix representation of your operator, and they will block diagonalize it into blocks that are uniformly sparse and well conditioned. So you can use an iterative method to invert that block diagonal matrix, and you can do it efficiently. Now, because these subbands are orthogonal in operator scalar product, you can solve your linear system LU equals F independently in each one of them. And in fact, what these wavelets have done is that they have decomposed your linear system LU equals F into independent linear systems that are uniformly sparse and well conditioned. Okay. And at the end of the day, again, you get a deterministic algorithm whose complexity is n polylog n, where the power in the polylog is the dimension of the space plus 1. And this is to achieve grid size accuracy in an energy norm. Now, before I show you another application, let me show you an example of this multi-resolution decomposition over these subbands. So here U is the solution of this divergence form elliptic PDE. And what you see here are the subband solutions or subband projections of U, right, on the subbands formed by these wavelets. The numbers that you see below those figures correspond to the relative energy content in each subband. And here this relative energy content decays very quickly towards 0 because we are taking a right-hand side that is regular. So we have a numerical homogenization phenomenon, and the energy put into the finer scales decays towards 0 very quickly. So you don't need to compute all the subband solutions. This is another example where the right-hand side is the mass of Dirac. So what you see here is, in fact, the decomposition of the Green's function. And here the decay in energy is at a much slower rate. In fact, you have to compute all of them because the right-hand side is singular here. OK. Now, let me illustrate this Gamlet transform and solve by running the algorithm for you. So in practice, the algorithm is not applied to the continuous PDE, but to the discretized version of the PDE. So you have your PDE and you have a fine mesh. We are going to assume that A is piecewise constant on each tet of the fine mesh. Now we assume this A is rough, so in practice this means that your conductivity A can be anything you want on each little tet of the fine mesh, provided that it remains bounded from below and from above. And we are going to discretize this PDE using, for instance, piecewise bilinear finite element methods. Okay. Now the algorithm is going to take 3 inputs. Those inputs are the stiffness matrix of the PDE using these finite elements. The second input is going to correspond to those interpolation matrices pi describing the linear dependence of the phase at level k minus 1 on the phase at level k. So for instance, if you are using Harpre wavelets, this will be one of the rows of pi 1, 2, and this will be one of the rows of pi 2, 3. So you have non-zero coefficients here, and here you have non-zero coefficients there. And the other input of this algorithm are these matrices W's that you will typically use to turn your Harpre wavelets into Haar wavelets. Okay, so here the coefficients that you see here are 0 here, and here they're just going to form vectors that are orthogonal to this guy. Okay. Now the algorithm goes like this. At the finest scale, you let your pre-wavelet psi be equal to the finite elements that you have used to discretize your PDE. And you take local differences of these guys with these W's, with these coefficients, to get your chi's. Okay? And those are going to be your orthogonalized wavelets. Once you have your orthogonalized wavelets at level 7, you can go on computing the corresponding subband solution using a finite element method in that subband. And you can do so by inverting this matrix B that is well-conditioned and sparse, so you can do it fast. You get your corresponding subband solution. Then once you have that subband solution, you take your level 7 pre-wavelets and you coarse grain them to level 6 pre-wavelets using those interpolation matrices R. And this R is sparse, so you can localize this computation and you can do it fast. And in doing so, you get your level 6 pre-wavelets and also your level 6 homogenized stiffness matrix or homogenized operator. Once you have your level 6 pre-wavelets, you can take local differences of them and you get your orthogonalized level 6 wavelets. And once you have your level 6 wavelets, you can go on computing the corresponding subband solution by inverting this linear system that is well-conditioned and sparse, so you can do it fast. Once you have your level 6 pre-wavelets, you can go on computing your level 5 pre-wavelets by computing this interpolation matrix, which is again sparse, so you can do this fast. And then you can go on orthogonalizing those pre-wavelets into orthogonalized wavelets chi's. Once you have chi's, you can compute the corresponding subband solution by inverting this linear system that is sparse and well-conditioned. I think you can get the idea. Then from level 5 pre-wavelets, you can go to level 4 by computing this interpolation. And then you orthogonalized, you compute the corresponding subband solution, you upscale, you orthogonalize, you compute the corresponding subband solution, you upscale, you orthogonalize, you compute the corresponding subband solution. And the last step, you upscale to level 1 pre-wavelets, and those are actually wavelets at level 1, and you can compute the corresponding subband solutions. And once you add all the subband solutions together, you get your the solution of UPDE and the corresponding multi-resolution decomposition. Okay. Now, let me move on to another classical problem in numerical approximation that we are going to address with this approach. And this problem is a problem where you would like to compute with dense kernel matrices, and this is a joint work with Florian Schaffer and Tim Sullivan. Let's go back to our operator L, okay, that we assume to be arbitrary continuous positive symmetric linear bijection from HS0 of omega into H minus S, and we assume it to be local. And let's call G its Green's function. Okay, so G is the inverse of L. Now, let's assume that S is greater than the dimension of the space over 2, so this Green's function is continuous. And let's consider n points in that domain omega that we are going to assume to be approximatively homogeneously distributed. Let's call them x1, x2, xn. And let's call theta the n by n symmetric positive definite matrix that you can form by looking at the evaluations of G at those points xi and xj. Okay? So you get a matrix theta that is n by n and dense. Now, such matrices are important in computational physics. So there you will see them as describing the interaction between pairs of electrons. They appear in Gaussian process statistics when you try to compute, when you have a maximum likelihood method, or you want to compute the log of the determinant of this matrix. They will also appear in kernel methods for machine learning or support vector machines. So in that case, you have to invert this matrix theta that you call a covariance matrix. Or you may want to do PCA on it, and then you have to essentially diagonalize that matrix. And the question is, how can you do it fast? Now, since theta is dense, naively, if you just want to store it, you are going to pay a cost n squared. If you want to do matrix vector multiplication, you're going to pay n squared. If you want to compute theta minus 1 times the vector, you're going to pay n cubed. If you want to compute the determinant of theta, you're going to pay n cubed. And if you want to compute the PCA, the principal component analysis of theta, you're going to pay n cubed. And what I want to show you here is that given epsilon, a parameter epsilon, and knowing only omega and those points xi, so you don't assume that you know the underlying covariance function G or the underlying operator L, you can select n polylog n entries of theta. So theta has n square entries. We're going to look only at n polylog n of them. And ordering p of those points xi's. From these entries, we are going to compute a lower triangular matrix that we are going to call L, such that the number of non-zero entries of L is of the order of n polylog n. And the claim is that you can do so in complexity n, polylog of 1 over epsilon, in time and space, in a manner such that you can approximate theta by this Cholesky factorization to an order of accuracy epsilon. Okay? And this allows you to approximate all the operations that I have mentioned previously to the accuracy epsilon in n polylog n complexity. Okay, so what I want, this algorithm is extremely simple, so I want to show it to you. And I want to show you why it's working by looking at the interface again between numerical approximation and Gaussian process regression. Now, what is the algorithm? Well, the algorithm is very simple. You just take your endpoints xi and you decompose them into a nested hierarchy. So what do I mean? You decompose them into coarse points, then finer points, then even finer points, and so on and so forth. So basically what you are doing here is that you are selecting subsample of these points, and some subsamples you call them coarse, some other ones you call them fine, even finer, and so on and so forth. And this induces an ordering in your set of points. Then with this ordering, what you are going to do is that you are going to define a sparsity pattern that is going to allow you to ignore most of the entries of that matrix theta that has n by n entries. So it has n squared entries. We are going to ignore most of them. And the way we're going to ignore them is like this. So where first we look at the coarse point and say that we select one of those coarse points. And this is our matrix theta, but in that matrix theta, we are going to keep the entries ij corresponding to the interaction of that point I with all the points j that are in this disk of radius 1. Okay, so those are all the corresponding entries of the matrix theta. We do the same thing for all the coarse points, then we move on to the next level of resolution of those points. So we look at the green points, but here what we do is that we divide the radius of that disk by 2. So we are going to look at the interaction of this point I with only the points j that are within that smaller disk. And those are the corresponding entries of the matrix theta, so we have less of them. We do the same thing for all the green points. Then we move on to the next level of resolution of points, so the brown points. And again, we divide the radius of the disk by 2, and we keep even a fewer number of entries of the matrix theta. Okay? At the end of this process, what you have done is that out of this matrix theta, you have extracted a matrix gamma that corresponds to only to some of the sub-entries of theta, and what you are doing is that you're only keeping n polylog n entries out of that dense matrix theta. Okay? Now, the algorithm is very simple. You simply use the Cholesky factorization that you apply to theta, but what you do is that you skip all operations in which these entries, kj's, ki's, ji's, or ii's, are outside of this sparsity pattern that we have defined. So basically, you skip most of the operations that you see in this Cholesky factorization. So what you obtain is an incomplete Cholesky factorization where you are skipping most of the steps of this Cholesky factorization algorithm. And what you see here running, this is the complete Cholesky factorization running. This is the incomplete Cholesky factorization that is running. And this one is running much faster because you are skipping most of the operations, and in fact all the operations that are outside of this sparsity pattern. Okay? And one point to observe here is that the algorithm is oblivious to the exact knowledge of the underlying PDE and uses only the geometry of the discretization. So basically this thing is saying that there is something universal about elliptic operators. They are essentially all the same. You can use the same method to address all of them. Now, why does it work? Well, it works because this matrix theta has almost sparse Cholesky factors if you use that ordering. Now the question is, why does it have sparse Cholesky factors? And to understand that, you have to use these gamblets or these operator-adapted wavelets that you have derived from this game-theoretic approach to numerical approximation. More precisely, you are going to look at the gamblets associated to masses of Diracs taken as measurement functions. Now, what is the relationship between the two? Well, if you take your phis to be masses of Diracs centered at those points xi's, then you can show that the inverse of this matrix theta is actually the stiffness matrix of those psi's. Okay? And what we are going to do here is to use this operator-adapted wavelets to represent elementary linear algebra relationships and elementary linear algebra operations, and we're going to learn something about them. Now, so we have those phi's at level Q, and what we are going to do is that we are going to turn them into a hierarchy by subsampling them. So we get our subsample Diracs. And what we have to observe is that this hierarchy of phis induces a hierarchy of submatrices of theta that we call theta k. And it turns out that a single step of the Cholesky decomposition is in fact computing the Schur complement of the block theta k minus 1 of the matrix theta k. And that single step corresponds to the inverse of this matrix bk that we have seen before, and that we have seen that it is well conditioned and sparse, so the inverse is sparse and also well conditioned. So this is in fact how you get sparsity by going through this incomplete Cholesky factorization. Okay. And in fact, the entry ij of that matrix is also related, is equal to the conditional covariance between your Gaussian process at the points xi and xj condition on all the other points at the next level of coarseness. So this is the relation with information, with the Gaussian process regression. And I will stop here. Thanks for your attention.
Question from the audience?
Yes?
So when you're selecting points for this last section where we're trying to, so the algorithm that I understand is I'm going to select some points, and then for each one I'm going to define a window around it, and anything that falls in between I've got to compute it.
Yes, yes.
You didn't tell us anything about how you're selecting those points, and what I'm wondering is it possible to formulate a strategy so that the fewest number of interactions have to be computed, and can this do something to improve the sparsity of the results?
Mark, can you repeat the question for the microphone?
So the question is, so if you look at the way the algorithm works, is that you have to take your points and turn them into a hierarchy, right? And so you have to choose so those are all the points, they're all drawn in blue here, and you have to select a subsample of them and call them coarse, and select another subsample of them and call them next level of resolution, okay, and so on and so forth. And the question is, how do you do that? How do you do that efficiently, right? Is that your question?
Yeah.
So you typically, basically those points do not need to be on a regular grid, okay? The only thing that you need about them is that the distance between them is bounded from below and from above by, so if you're at this level 1, by 1/2 times the constant from above and times the constant from below, right? So you can put a ball around this point that doesn't contain any other red point, and you can also put, and if you can also cover this whole thing by balls of radius 1/2 times the constant. You need something like that, and you need the same thing for the green points, but here so I'm including those, okay, in the next level of resolution. But here the ball is, instead of being of size 1/2, is going to be of size 1/4. So my point here is that those points do not need to be on a uniform grid. You can perturb them around. They just have to be roughly homogeneously distributed at each scale. Okay. So how can you do that? Well, if you're on a low dimensional space, this is fairly easy. You can just use nested dissection, and you just select points here and there. If you are in a higher dimensional space, the equation is a bit more involved. Yes.
So actually, I was going to ask you on the high dimensionality.
Yes, yes.
If you try to, as we know, sparse grids and all of these techniques,
yes.
just to continue this, they have a problem, the way they scale in high dimensions.
Yes.
It doesn't really work properly, okay? So can you do this in going, let's say, 2 or 3?
Yes. So you can implement that. So if you look at the algorithm doesn't really care about the algorithm doesn't know what the underlying Green's function is, G, right? It's just and it doesn't know what the underlying operator L is. It's just looking at the physical locations of these points. So in practice, you can also apply it for high-dimensional problems. So your question is, how would it work? Well, empirically, in the complexity of the algorithm is n log n, and in the log you have the power 2 times dimension plus 2. So for rigorous results, the dimension of the space will enter as a power in the log. Now, empirically, you can also apply to high-dimensional problems, and what you will observe is that if your data is in a high-dimensional space but living in some kind of low-dimensional, not too high-dimensional submanifold, the method will work well. And it will find that kind of manifold for you. Now, how far you can, so for instance, this is an example where your data, in fact, lives on a 2-dimensional manifold in a 3-dimensional space. You can imagine that, in fact, this could be a 2-dimensional manifold in, 2,000-dimensional space, and the method will still work. It will still work there.
So this incomplete Zalewski factorization, have you seen any similarity in, I suppose maybe Steve was thinking of this, with the way they compute inducing points in Gaussian processes to explore sparsity?
What do you mean?
I don't know if you, well, basically the idea is if you have millions of data, you don't really need all of them to define the Gaussian process. A subset of some critical points can do the job, and in principle what you do is you do some incomplete factorization of the covariance function.
Yes.
So are these related?
Well, yes, because I mean, once you have the Zalewski factorization, once you rack your covariance function G as L transpose, you know that you can take a Gaussian vector with entries that are n01 and independent, multiply L by this vector, and you get a representation of your Gaussian process, right? Now, if L is sparse, then you have a sparse representation of your Gaussian process. So you can use that for that. You also have it, in fact, from so you have it from the Zalewski factorization perspective, but you also have it from the perspective of these operator adapted wavelets that are presented in the beginning. Why? Because you can actually show that I don't know if there is a pen here. So you can actually take your Green's function, and if you use this operator adapted wavelets, you can decompose it. You can what you're going to have is a sparse rank revealing representation of your Green's function. So you can also use this operator adapted wavelets to get a sparse representation of your Gaussian process. You can also do that.
We do know that some of those have some problems, but we're going the time. We'll discuss another time. Any questions? Any other questions? Thank you, Houman.
Thank you.